Today we want to prove that this huge product of factors is not a multiple of 10. And I'm just going to quickly point out that there are 20, 24 minus 3 plus 1 factors, right? And y'all, by factors, I just mean the object i+1 cubed, okay? So that's equal to what, 2022? Yep, can handle that arithmetic. 2022, there's 22 factors, and so it would be a pain to try to multiply this out. In fact, if not impossible in our lifetimes, to multiply it out and ensure there's no errors. We want to show that this product is never a multiple of 10. In other words, another way of saying this, it's not equal to 10m. Okay, it's just I like using the congruence operators here. Now, so notice that 10 is equal to 2 times 5, of course. 10 equals to 2 times 5. See, and so as long as we can show that this piece right here, this guy right here, is never a multiple of 5, there's no way the product of the 22 factors could be a multiple of 10. Okay, so let's keep going. Now, y'all, this result right here is just, if you expand this out, remember the binomial theorem or Pascal's triangle, you get 1, 3, 3, 1. That's what happened right here. It's useful to factor this expression like in this fashion just for computational reasons. So we're going to do this via modular arithmetic. We're going to show that this is never congruent to 0 for all I. And all you really have to do is check for I equals 0. Let me just write them down. For all the possible remainders when you divide an integer by 5. Okay, so if I is equal to 0, and I'll just substitute directly into here. What do you end up with? That we get a congruent 1, right? Okay, if I is equal to 0, this whole part vanishes, and so we just have congruent to 1. All right, and then so I equals 1. If we put 1 right here, we get what? 3 times 2. 3 times 2 is 6 plus 1 is 7. Okay, so that would be congruent to 2 mod 5. And again, folks, just to double check myself, if I is equal to 1, if you put a 1 here, you get 3. If you put a 1 there, you get 2. And so 3 times 2 is 6 plus 1 is 7, but that's congruent to 2 mod 5. Okay, this congruence mod 5. All right, so let's keep going. Remember, we just have to check for the 4 remainders, or we just have to check in the smallest residue class, they call it number theory. So for I equals to 2, we get 6 right here, times 3 is 8, 6, or 3 times 2 is 6, times 3 is 18 plus 1, that's congruent to 4. 19 is congruent to 4. Mod 5, again, y'all, I'll double check the arithmetic right now. If you put I equals 1 right here, you get 3. And then 2 plus 3, whoops, let's see here, 3 times 3, oh, I'm sorry, 6 times 3 is 18, plus 1 is 19, and that is congruent to 4. Okay, so I equals 3. I equals 3, 9 right here, 3 times 3 is 9. 3 times 1 is 4, so that's 3 times, I'm sorry, 9, I can't do this, y'all, 9 times 4 is 36, plus 1 is 37, so you would get congruent to 2. And again, y'all, I may be making mistakes here, I hope not. Now, and so, and finally, we'll do I equals 3, I equals 4, excuse me. And again, y'all remember, notice we just did all the possible remainders. I equals 0, I equals 1, I equals 2, I equals 3, and I equals 4. Now, if you put I equals 4 into this expression, you get 12 times 5, which is 60 plus 1, and again, you get a congruent 1. 61 is congruent to 1 mod 5 because 5 times 12 plus 1 is 61. Okay? But y'all, the key aspect of all of this is that we never got 5. In other words, it was never, none of these ever were congruent to 0, mod 5. Okay, so we finished our proof. Okay, y'all, that's it. And I may have made some mistakes on the congruence arithmetic. I don't think I did. We just showed demonstrably that all all of these factors are not multiples of 5, hence they can't be multiples of 10. So that finishes the proof. Okay, thanks for viewing.